Our first speaker, I'd like to introduce Damien Harty, who is Senior Research Fellow in Vehicle and System Dynamics here at our Engineering and Computing faculty, and his talk is entitled Dynamic Obstacles and Solutions to Novel Vehicle Layouts. And Damien will challenge the future sustainability of 5- and 7-seat vehicles, and he'll look particularly at active control technology as a potential solution. Thank you, Damien.
Thank you. Thank you for inviting me to come and speak. I'm going to kind of wave my hands a lot and just try and float some fairly interesting notions. I'd like to say before I start that if I had all the answers, I'd have started my own company while I still know everything. So I'm not proposing that I have all the answers, but I think our role is to start trying to work out what some of the questions are. And it's important when we're doing that we're mindful of some of the things that have changed recently, some of the rules that we've been used to about making stuff. Some of those are no longer in place. So I'm going to dive straight in, and as we've kind of already discussed, there are various pressures and challenges facing cars. And one of the big ones for me is the fact that when I want to go somewhere, everyone else in the world also wants to go to the same place, and I have to wait behind them. And I don't know about you, but that drives me bonkers. And my solution to it is to travel by motorcycle. And some of you saw me earlier this morning, would have seen me in leathers and a helmet, and I went and found a telephone box and got changed into something a little more appropriate. That's not suitable for everyone, and there are various objections to that. But basically, we have a problem in that everybody wants to go to the same place at the same time, and that's more or less baked into our society. In order to generate the wealth that we're all used to, we have to cooperate, and a large amount of that means going to places of work in regular patterns, which means that the only time we have for leisure time is at the same time as everyone else has leisure times, and so on. But one of the issues that I see is that we have this persistence in wanting a 5- or 7-seat vehicle for all of our journeys. So we size our vehicle for perhaps one journey a year, and then the rest of the time we're driving around in this vehicle. And I'd suggest a challenge to you, any of you who travel to work at a regular time and who travel to work at the same time as everyone else, try and spot a car with 2 people in it on your journey. However you make that journey, try and spot a car with 2 people in it, and you'd be amazed at how few there are. Globally, the sort of vehicle occupancy is about 1.6, and of course we've all got exceptions to that when we go on holiday and so on that mean we justify our ownership and use of these large cars all the time. But you know, that's one of the things we have to challenge, I think. Some people have done some work. GM did some work in the 80s actually about what if you did you introduced some vehicles that were more mobile, that could lane split, as the Americans call it, in the way that motorcycles filter through traffic. What does that do to traffic flow as a whole? And the results on that were very clear. A relatively small amount of more mobile vehicles significantly improve the traffic flow. You don't have to have everyone having one. You only need something like 10 or 20% to something like double the kind of average traffic speed. It really does make a very, very large difference. And the other problem that we've talked about is the energy one. Now, I'm not going to talk about is it carbon dioxide or what. The point is there are a lot of us, and at the moment we consume a lot of energy, and that is going to increase, as Peter has outlined. And when it comes to the personal transport problem, we've all become a bit spoiled with hydrocarbons. I deliberately write the numbers in non-scientific notation so that you can see all the zeros. 40 million joules in a kilogram of hydrocarbon. And if I can just try and make that real for you, this is a kilogram of liquid. That's a kilogram of liquid. And if you imagine the same mass of petrol, which is, you know, broadly the same, it's a little bit more than water because petrol's a bit less dense, but it's broadly the same. That is enough to lift 40 million apples a distance of 1 metre. So that's a very large percentage of the UK population all lifting an apple at the same time through a distance of 1 metre, that there's enough energy in 1 kilogram of hydrocarbon to do that. And we're typically sloshing tens of kilograms into our vehicles on a pretty regular basis and very blithely driving around. And we're recognising that we can't carry on with hydrocarbons, and so we're looking for other stuff. And everybody talks about batteries and how it's no problem, we'll just switch to battery cars. But the big problem with storing energy in batteries is that you only get about 1% of the storage that you do in hydrocarbon. Now, some of that is offset by the fact that using hydrocarbons to move the vehicle is horribly inefficient. Again, Peter's already set the stage by saying that 80% of the energy we put into the vehicle, basically we throw overboard and we don't get it to move the vehicle. So that's pretty rubbish from my point of view. I'm kind of, I'm not proud of that as an engineer. But that is how it is with internal combustion engines. Electrical vehicles tend to do much better in what people call the tank to wheels efficiency. So although you get a lot less energy in, you do at least harvest a lot more of it to move the vehicle. It's not the kind of 99% that some people would have you believe. You do still lose some energy from on board. And hydrogen's somewhere in the middle. And we were having a discussion in the interval about hydrogen is great, but it's an energy carrier, it's not a fuel, and where do you get it from? And there's quite a lot of big questions around all of this stuff. And so for both of those reasons, it seems to me that we've got to make a very large change. And I'm not talking about what if we made a 5 kilogram suspension knuckle 1 kilogram lighter by making it out of aluminium, which, by the way, is a disastrous thing to do from an energy point of view because it costs a lot of energy to get aluminium compared to getting cast iron. I'm not talking about footling around with a kilogram here and there. I'm talking about really moving the needle, because the thing that I see is that we are perfectly accepting of the fact that we are bringing along 1,500 kilograms of vehicle with us in order to move one 75 kilogram person. I might be a little more than 75 kilograms, but if you bear with me, it makes the mental arithmetic easier. That's rubbish. I'm 5% of the mass of the thing that we're moving. And if you look at that, 20% of the energy that we put on board is actually manifest in moving the vehicle. If you look at 5% of that 20% is moving me, that means that 1% of the energy that we put into the vehicle actually accomplishes its primary task, which is to move me around. So at the moment, we're 99% inefficient. And I feel like we're quite clever. I'm really sure we can do better than that. And the difficulty for me is that it's not obvious how we do that. We've been making engines, for example, for 100 years. We're very practiced at it. There are people who are very good at it. We've got fabulous manufacturing processes. We can turn out very large numbers of them to very tight tolerances. They do marvelously clever things. The idea that I might sit down and work out a way to double the efficiency of an engine is quite unlikely. And we're on that sort of diminishing returns curve for a lot of the technology that we're currently employing. So the idea that we're just going to miraculously double efficiency, certainly with internal combustion engines, is unlikely. And there are, we're at the start of the journey with other stuff. But I want to come back to this idea that we need so much mass of vehicle to transport me around. And as I said, I came here on a motorcycle, which has a much more favourable ratio, but they're not for everyone. But one of the things we might be able to do is perhaps make half a car. Instead of having a 5 or 7 seat car, perhaps we could acknowledge the fact that we don't need an entire car for all the journeys we make. So if you're going to make half a car, if I imagine it as a box, well, let's just imagine cutting it in half. And one of the obvious things you can do is kind of cut it in half horizontally and just make it half height. So there's a beautiful thing, this what Volkswagen called the 1 litre car. It's 1 litre per 100 kilometres, which is fairly phenomenal fuel consumption. And when you see the thing physically, The seats are like something out of a sailplane. You know, the whole thing is a work of art. It is like a beautiful lightweight sailplane, and there's been meticulous attention to detail. And it still uses an internal combustion engine, but the point is that that platform has very, very reduced energy demands compared to you know, a 1,500 kilogram car. The problem with low weight, or low height rather, is that people don't like it, and everyone giggles a bit at the C5, but Sir Clive was trying his best to do something. He maybe just had never been in one of his own things next to a London bus, and that was a thing that people pulled out fairly quickly, is that being low is really quite terrifying. And so if you look at the fact that people will choose a Nissan Qashqai over a Nissan Micra, it's kind of telling you that height is something people like, and you're not going to get them to give it up. When you talk about mainstream vehicles, it's going to be difficult to get people to give up height. So another one might be, well, what if you just make the car half length? And a smart car is quite a good example of that. The BMC Mini is a phenomenally clever piece of packaging. It wouldn't pass current crash legislation, but it shoehorned all the bits that were needed into a really small space and a very lightweight. Part of its very lightweight was because the expectations for trim standards in the sort of late 50s and early 60s were very low compared to what they are now. So you had a large amount of painted metal surfaces, which are actually forbidden now by US head injury legislation. But part of it is that it is just a very small car. And this is a pair of smart cars in Rome. I recently came back from my honeymoon there, and I noticed these from the window. They're parked end on in the spaces, and so people are quite creative with how they park in Rome. And you can see that there's a kind of a half-length solution, and that's really good in terms of moving the needle for overall vehicle weight and therefore fuel economy. Regardless of the powertrain, taking weight out of the vehicle is a really good thing. It doesn't really help the aerodynamics much because you've still got broadly the same frontal area, and in fact when you have a very small car, the fact that it needs to go from no area here to the full passenger area in only about 1.5 meters, that becomes quite challenging to manage aerodynamically. And so you tend to find that you don't necessarily get the aerodynamic benefits that you expect when you downsize the car. It doesn't really help you with congestion though. You can't really filter between the gaps. So although it addresses one of the problems, it doesn't really work on the other problem. So the other dimension is to cut the vehicle in half lengthways. If you can sort of, imagine me taking a bandsaw to the microcab here, or the little Peugeot. What if we make it only 1 meter wide? So it's the same height, so nobody's frightened. It's the same kind of length, so that you've got room for 2 seats, one behind the other. Because although I say most journeys are made with one person, the occasional ability to carry a passenger is reasonably important, and even on a motorcycle it is important. It does fantastic things for vehicle weight. If you look at a motorcycle, that's only 1/4 of a tonne. Obviously the trim levels on a motorcycle are very low, and there are some disadvantages in terms of getting rained on, which I've been thinking about quite a lot recently. But on the whole, it's really good. The blue bike there, which is not dissimilar to the bike that I came on this morning, has faintly ridiculous levels of performance, and yet still returns better fuel economy than a turbo diesel hatchback. The little red one at the bottom is a fairly bonkers thing made by what calls itself a company but is really one guy, the Commuter Car Corporation. It's a vehicle called the Tango. And it's got 1,000 kilograms of lead acid batteries under the floor, and that's how come it doesn't fall over, which is sort of great, except that what I was trying to do was get rid of a load of weight, and so for me that one doesn't do it. But you've got a sort of intriguing vision of the kind of form factor that you could have there. It's tandem seating, it sort of looks like a car, but there's just a lot less of it, and you can imagine being pretty cheeky in traffic with that, in the same way that I am with my motorbike. There is the small disadvantage, though, that if you haven't got 1,000 kilograms of ballast, then it tends to fall over, and it's difficult to get that really narrow width. And the motorbike has that disadvantage as well. Any of you who've ever sat on a motorbike at a standstill and forgotten to put your feet down, you will have had the experience of falling over. Or one of the things that I've done, I think every motorcyclist has done it, is you go to lean the bike on the stand and then you realise that you haven't put the stand down. And just as you realise that is the point of no return, and you just have to let the bike go. So this kind of falling over business in corners is quite an issue, really, with a narrow vehicle, which is a shame because in terms of the things I was trying to do, a slim vehicle, a tandem layout, feels really appealing. So if all we had was the technology that we've always had, at that point you would rule it out and say, well, sorry, these vehicles are as good as it gets. The other thing that's important about the vehicle, which is why the motorbike is no good, is it has to pass the bridesmaid test. This is a friend of mine, Annalie, a lovely lady, and she was bridesmaid at a wedding, and I can't remember how or why I persuaded her to sit on my bike to take a photograph, but anyway, I did. It's really obvious that she couldn't go to the wedding dressed like that, and in fact, most of us can't really live our lives if we have to turn up with helmet hair and leather clothes. It adds a level of inconvenience to my use of the motorbike, and I'm quite determined, so I overcome that, but it's not for everyone. And the kind of the bridesmaids test is quite important. So if you can sort of imagine something that somehow magically overcame the falling over problem, passes the bridesmaid test, which that vehicle does, then suddenly we've really moved the needle. We've taken a bucket load of mass out of the vehicle. So all of the things that Peter mentioned, we've improved significantly, particularly the urban fuel consumption. The rolling resistance is greatly affected because rolling resistance is very sensitive to mass as well. And if we do it right, we've improved the aerodynamic picture as well. So we've really kind of dramatically moved the needle in a way that doesn't really need any new powertrain technology. And more importantly, it reduces the demands on any emerging powertrain technology. So rather than having to carry enough energy round to take the 1,500 kilograms of vehicle with us, which rapidly turns into 2,000 kilograms of vehicle by the time you add a load of batteries, rather than having to do that sort of mass-based tail chase, we actually start off with a much easier question. Unless either we go really slowly or or we just don't go around corners, the vehicle's got to lean. In order to make a very narrow vehicle work, it's got to lean. And so immediately there are a couple of choices. You can have a device with some hydraulics to tilt the vehicle. This is a restyled Van den Brink Carver. I think Jeremy Clarkson described the Carver as the most fun you could have with your clothes on. I'm not completely sure about that, but I think maybe he doesn't ride motorbikes, so I'd say there are some experiences that might be better, but it is certainly a lot of fun. And the sensation of banking into corners, for me, is not remarkable. It works very well in a closed cabin. It's not at all weird. You very quickly become acclimatized to it. So you can do that. One of the issues with that, though, is kind of weight and complexity. All of that weight you took out, you've added a certain amount back in. It's not too bad. Because you get very high energy density with hydraulic systems, so you can put in the kind of power that you need, but it still consumes some stuff. But another alternative is a free-leaning device, which basically uses the same dynamics as a motorcycle. And there was a chap called Kaleha who put this little prototype together some time ago now. And it's a delightful thing. And in fact, there are production scooters now with two wheels at the front, which employ the same principles. And you can lock up the roll articulation as you come to a halt, and that means you don't have to put your feet down. And what that means is you can have the scooter with a kind of a spray deck. And you see some of these in London now. They've got a sort of a spray deck, a bit like a canoe. And so your lower body can be really quite well out of the rain. You're still in the rain, but it doesn't require much of a sort of a leap in thought technology to imagine a cabin, and you know, a cabin a bit like the Carver cabin, but on this sort of platform. The problem with it is that when you lock it upright, you've got to steer it like a car, which is very kind of geometric. You turn the wheel and the car goes that way. But when it is leaning, you've got to steer it like a bike. And a lot of people get a bit confused about how motorbikes work, and they imagine it's some sort of gyroscopic magic. It isn't gyroscopic magic. It's just like balancing a broom on your hand. So when you want to go right on a motorbike, what you do is you push slightly on the right-hand bar. That has the effect of steering the motorbike a little bit to the left, but because it hasn't got any width, that makes it fall over. And when it falls over, you release the bars, the steering geometry takes over, and you go round the corner. And this kind of force-based steering, and steering the wrong way, that's the thing you had to learn when you were a child and you couldn't ride a bicycle. You may remember that one day you couldn't ride a bicycle and the next day you could ride a bicycle, and now you can't replicate your performance of not being able to ride the bicycle. The only time it comes back to haunt you is if you either swap hands like that, or you go to London and there's one of those reverse steer bikes and the chap will give you 20 quid if you can get 10 metres on it, and nobody can. So that mode of operation you can do, but it's really difficult to swap instantly from one mode of operation to the other. And quite a lot of people have done work on this sort of thing. It's ever so easy to knock up a thing mechanically that will work, but it's ever so difficult for an untrained, unrehearsed operator to use it in a safe and reliable way. So what about if we had a steer-by-wire system? Now, by wire, when I talk about by wire, some people think I mean doing what we did before but with electrical actuation instead of hydraulic, and that's not what I mean. I'm talking about having no physical connection between the thing that I touch and the thing that moves. I'm talking about it being electronically controlled, and I don't actually care how the thing is moved, but I'm talking about it being computer controlled. And that allows us to go back and ask this question again about the half-width vehicle. We couldn't do it before because we couldn't overcome this fundamental inability that human beings have to swap modes of operation and modes of control. But what if we ask the computer to do that? What if we ask the computer to recognise that the vehicle has switched from one configuration to the other and change what the steering wheel does? So all we ask the human to do is, if you want to go right, move the wheel to the right, and the computer takes care of everything else. And that opens up quite an interesting possibility. And this is a multi-body system model, a predictive model that I made of such a thing. And you can see, even when it's travelling quite slowly, as you can ride a bicycle, you can make it lean. And then when it goes down to kind of walking pace, it locks upright and it steers just like a car. And it'll arrive again slightly from the right and going a bit more quickly and banking into the turn. And the computer program can swap between those two modes of control, and it's not that difficult. And in fact, you can engineer the software to make that transition. So again, I'll just emphasise, I'm not saying this is the future, but what I'm saying is that the ability to do this stuff, this by-wire control that we didn't have previously, it's allowed us to go back and re-ask a question that previously we'd dismissed. And I find that very interesting. A few years ago, Coventry University did some design studies on such a thing because it's all very well it being technically possible, but as Steve mentioned, we've got to get people to want it. And the question is, could you get people to want it? And we set them a fairly challenging brief. We said that you've got to tear up all your preconceptions. And one of the things that came out very strongly was these bumpers that we carry around so that we can park and bump into each other and all of that. If you've got a really light vehicle, on a motorcycle, the tyres are the bumpers because the wheels stick out. There are some pedestrian legislation issues with that, but there are ways around them because you can do it for a motorcycle. But that's a great way of just deleting a load of weight from both ends of the vehicle, which you're only carrying around with you just in case. So you can make each bit of the vehicle do more than one job, and using the wheels as bumpers is a good example. And we ended up with some pretty funky design studies. And when you look at the actual shape of the vehicle, the distance between you and the extremities of the vehicle, there's still room for all those side airbags, the cushion airbags that we're used to, the curtain airbags. There's still room for a metre of ride down in the hardware for the sort of offset deformable test and so on. And the vehicle as a whole is a lot lighter. Now, there are always issues with compatibility with heavier vehicles, with such things, but those issues are not going to go away. And the truth of this is not something that people like to hear, but if you're in a Ford Fiesta and you're hit by a 40-ton lorry, it's very bad because the Fiesta only weighs 1 ton and the lorry weighs 40 tons. But if you do the maths, you'll find that 40 tons is a lot more than 2 or 3 tons in a Jaguar as well. And so the truth is that if you're in a very large vehicle, it doesn't help very much if you're hit by a 40-ton vehicle. And the best thing is not to get hit by the vehicle. And this is the kind of the logic that I apply when I'm riding the motorcycle. I'm deeply aware that I'm very vulnerable, and so I say the safest thing is not to crash. And I've got a vested interest in not crashing, and that really changes my mental outlook when I'm using the vehicle. Now, clearly we can't rely on everyone to do that, but what I'm saying is that having bigger vehicles isn't the answer to the compatibility problem, because if you pursue that to its logical extreme, we all end up driving Sainsbury's lorries, and that's no good. So we've got to find another issue, a sort of a social answer rather, to the compatibility issue. But as you can see, it's a pretty funky thing, and that's great, but all of that so far has all been a thought experiment. And the real question is, does it actually work? And I had the extreme good fortune of being indulged significantly by my previous employer, and we were able to make a mule. Now, it's not very pretty, but that's because it was a mule. It was a very interesting experience. First of all, we put it together as a really straightforward mechanical thing, and because I was obsessed by it and had been obsessed by it for a long time, I had no bother riding it. I could easily make the switch because I knew when it was coming. I'd written the software that made the switch between upright and leaning and so on. And so it was basically very easy for me to maneuver, but nobody else but me could ride it. Nobody else. And we had a lot of hilarity with the vehicle diving off onto the grass and people pulling it back and so on. Nobody but me could use it. So then we went to the next stage, which we got a little power steering motor out of I think that's a picture of a Corsa motor, but we got it out of a small Subaru. It's a very ordinary EPAS motor. They're produced in huge volumes. They're really quite cheap. We reverse engineered the kind of communication protocol for the motor and added some power electronics so that we could work it very proportionally. It's quite easy to imagine 2 of those in the vehicle. You've got a large number of small electric motors in a modern vehicle. At the very least, you've got front and rear windscreen wiper motors. It's now cheaper to make electric window lifts than it is to make manual lifts. So, high volume, relatively low power electric motors are quite readily available. And really normal instrumentation on the vehicle. All of the stuff that you've got on the vehicle already, wheel speed sensors, yaw rate gyros, all of that stuff for your ESP system, it's all automotive standard, production ready, signed off for minus 40 degrees and all of that stuff. There was nothing controversial about it at all. And I was able to sit down and think about, well, what was I doing? What did I want a steer-by-wire system to do? And bear in mind that I had no physical connection between the hand wheel and the road wheels. I could write some computer software to do whatever I wanted. And you can see the little red man on the top. He's what happens if you get it wrong. And I did physically verify that that's what happens if you get it wrong, and I can say that was quite an exciting ride. The blue chap is when you get it right. He looks after himself. He's really very nice. And the algorithm's not hugely contentious or complicated. As a result of having done that, everyone could ride it. Nobody had any trouble whatsoever. Now, as I've said, I'm not suggesting that is the solution, and I'm not going to run away now and start the narrow car company. But what I am trying to illustrate is there's a whole load of stuff now that we can do that we couldn't do before. And in fact, I'd go so far as to say that in terms of vehicle design, we can do anything. If you think about a Segway, that's more or less a self-riding unicycle. And of course, Honda have had to go one better, and Honda have made a self-riding unicycle. You can just kind of sit it there and you can sit on it, and it will balance itself, and it's all computer controlled. And if any of you have ever tried riding a unicycle, you'll be really impressed with that. So we can do anything. We can do really anything from a vehicle point of view. The question is, what should we want? And how do we know what to want? And that's the question that I haven't got an answer to. But I'm really confident that we're very well placed to deliver whatever it is that we work out that we want to do. And a final point is that this is a time, as a lot of other people have mentioned, of phenomenal experimentation and diversity. And the last time there was that time was around about the turn of the century, 100 years ago. That's when there was that level of variety, and a direction emerged from it. But at that time, it was by no means apparent that the internal combustion engine would be the thing of choice. The fuel for it was horrifically dangerous. People were getting burned and explosions happening all the time because people didn't understand about petroleum vapour. You couldn't get the damn thing to start. It had no torque from a standstill, so you needed this clutch thing. It needed a phenomenal amount of skill to drive it, to manage the spark advance and the mixture control and all of that. The internal combustion engine was a real outlier at that point. And the loaner Porsche with some batteries and in-wheel motors was definitely looking like the horse to back. And yet, 100 years on, that proved not to be the case. But now, everything's up in the air again. And so, as a concluding remark, I'll have to say this is a fantastic time to be an automotive engineer. Thank you.
Many thanks, Damien. I thought that was a fascinating talk, not least because I thought it presented some interesting challenges around a phrase we don't hear that often these days, the joy of motoring, and how with those kinds of innovative systems one actually perhaps reinterprets the joy factor in terms of design. Moving on to our next speaker, Dr. Jeff Legood is an automotive aerodynamicist and director of GL Aerodynamics, and he's also a part-time lecturer in our automotive aerodynamics course in the Department of Industrial Design here at Coventry. Fascinating and retro title, The Teardrop Explodes. Depending on your age, that's either a rock group or it's a caption to a comic frame. And Jeff will discuss the contribution aerodynamics can make to efficiency and the wider implications of that. Over to you, Jeff.
Good morning. If that title means something to you, it dates you as well as it dates me. And I'll apologise for it straight away. It was only a working title to begin with. I was just sketching some ideas down one evening, and I was listening to the radio at the same time, and Teardrop Explodes record was on. So I wrote it down. It kind of reminds me of my student days here as well. So it all kind of tied in. And then I thought, well, actually, there's a little bit more to it than that. Because if you've not got any aerodynamics expertise or background, you probably intuitively know that a teardrop shape is kind of the ideal aerodynamic shape, isn't it? Well, actually, it kind of is and it kind of isn't. It depends how you apply it. In free air, for low speed, then yes, it works fairly well. But as soon as you start approaching the ground, which is effectively the pictures on your far right, the shape needs to be modified to get it to work as efficiently. And to some extent, that's really what automotive aerodynamics is all about. Okay, let's see. Okay, so when Brian asked us to do this talk, he actually set us all some questions to answer. And what I've tried to do is try to engineer a talk around those sort of questions. So I'll try and answer them, but add in some other aerodynamic background stuff as well. It's not a complete story. There's plenty of aerodynamics technology that there just isn't time to cover today. But I'll try and highlight some of the interesting things that are going on currently, and maybe in the future we can look at some more advanced stuff, which I think potentially some of these new technologies in vehicle design might just open up that field in the same way that Damien was mentioning before. Okay, so essentially the aerodynamics contribution to a sustainable vehicle is to reduce the aerodynamic drag, to effectively reduce that resistance to forward motion. Numerically, it can be expressed in an equation which is relatively simple, which says the aerodynamic drag force is equal to a particular set of numbers there, and I'll explain. So moving from right to left, so we have the density of the fluid. Well, that's always going to be in air unless you happen to veer off the road somewhere. So that's kind of a constant. Projected frontal area, we'll talk about that a little bit later, but it is kind of key, but it's something that to some extent is out of control of most aerodynamicists. The velocity. Well, you could actually reduce your aerodynamic drag by going slower. So, but I don't think that's kind of against the grain a little bit. So we'll kind of ignore that, and it kind of seems a little bit of a backward step to take. It's a bit like taking Concorde out of service as far as I'm concerned. So we'll leave the velocity alone. And the last one, the aerodynamic drag coefficient, something that's a little bit more difficult to understand. It's a number that it represents the relative aerodynamic efficiency of a shape. Okay, and I don't really want to go into it any more than that, than just say it effectively represents how good or bad a shape is from an aerodynamic point of view. Okay, so before we move on, I want to tell you some history, because it's always useful to know where you've come from, to know where you're going. Okay, so aerodynamics was pretty much important from the very early days. As soon as people started to grab a car or some kind of vehicle, they wanted to move as fast as possible. And this is actually an electrically powered vehicle, the first vehicle to reach 100 kilometres per hour. And it has some aerodynamic thinking in it, certainly in the body. The downside is that the driver's stuck out the way, and you can probably guess that there's quite a big aerodynamic penalty from the driver plus his particular scarf. Now, this is actually a mock-up in a museum in Turin, so I think there's a little bit of Italian licence going on there. But the point is, there was some interesting thought very early on. Just a few years later, Count Ricotti ordered a vehicle based on an Alfa chassis, and this is kind of the first teardrop shape that we see in vehicle design. Now, the interesting thing is, in literature, there's no explanation as to why they decided on that particular shape. There certainly doesn't seem to have been any research beforehand, but the inspiration came from somewhere, so that's something I've still yet to determine. But the interesting one was I found just recently there was a picture of a open-top version as well, which kind of seems to defeat the object of that really nice shape. But at least it gives you a bit of an idea of size and proportion. Pretty much the starting point, as far as most aerodynamicists are concerned, is the work that was done by a Hungarian guy who worked for the Zeppelin airship company, Paul Jarre. Now, Jarre was credited with shaping of the Zeppelin from its straightforward tube into something with a little bit more curvature along its length. And then, as motor vehicles started to become more and more popular, he devoted more and more time to looking at shapes that were particularly useful for vehicles, and that's when he started to apply some of his airship knowledge to what happens close to the ground. The picture on your far right effectively shows that development, and he and a colleague, Klemperer, basically they came up with the idea that if you make almost a half teardrop shape, you can get a relatively efficient performance out of it, okay, but the drag is still reduced, but we ended up with what's become a little bit of a holy grail, which is a drag coefficient of 0.15 for a vehicle on the road. Now, there's a key factor here, and that's the overall proportions of the shape, and I've kind of mentioned that there, and if you can bear that in mind, I'll talk a little bit more about it before. But effectively, to get that low drag shape, we've ended up with an overall length to diameter, which you can consider to be height or width, because they tend to be fairly similar for most cars, of around about 5:1. So Paul Jarre actually spent a little bit more time on cars and developed his own shapes. He built his own car. The one on the top right is actually one of his designs on a Mercedes chassis. The pictures in the top left, those four cars, they're cars for different companies actually, but they're all designed by Paul Jarre and his own company. And if you think that sounds a bit obscure and you may not have seen those before, well, if you've seen the advertisements for the Audi A5 recently on TV or in the press, you'd have seen a rebuild of one of Jarre's earlier cars as the so-called ugly duckling in the TV campaign. Ugly, well, that's kind of your choice or mine. Compared to what was around at the time, I would say probably not. But anyway, it was an interesting story, and it's good that it's had some exposure again. Okay, I'm going to probably quickly run through some of these things, but Jarre's ideas inspired a whole load of other cars. Now, what the pictures I'm going to show you are cars that were inspired by Jarre's original ideas, some of his patents, some of his published work. In some cases, there were fees actually paid to companies that took some of his ideas. There's quite an interesting story around the Chrysler Airflow, which is still under debate apparently. In the book about the Chrysler Airflow, there's no mention of Paul Jarre's ideas, but Chrysler did pay Jarre some money, so there's obviously a bit of a story there. But these, again, were very, very different to the majority of cars that were around on the road at the time. So although I'm going to show you a few shapes, don't think this was common. These were fairly rare, and in some cases only a few of these vehicles were built. The Chrysler Airflow was probably the first attempt to produce a mass-produced car with some kind of aerodynamic shaping. It's commonly thought that its shape was too revolutionary and the public wouldn't accept it to start off with. But again, if you read some of the stuff that came out of Chrysler, the truth was the car wasn't actually ready for launch when they did actually launch it. So they couldn't produce them in time, customers were kept waiting, and it was actually that degree of frustration that actually led to a lack of enthusiasm for the product. And just a few years later, the Lincoln Zephyr came out, which was kind of almost the same shape, but that was taken off in leaps and bounds. So whereas the Airflow went out of production within 3 or 4 years, the Zephyr continued on. Again, the ideas were taken by Porsche, Tatra, you might be familiar with those, particularly low drag car of its era, partly assisted by the fact that the engine's at the back, of course, so the intake and the cooling performance is different. But in general, some very interesting shapes. One of my favourites, really, on the Alpha 8C. Again, taking Jarret's ideas. And the interesting thing about this is the proportions of its length to height and width as well. Sadly, I've not got any aerodynamic data for it, and very few of these were produced. I think just 8 in total. But if anybody's got one and would like to lend it to me to take to the tunnel, then I'll quite happily test it for you, so long as I get to drive it there as well. But again, applying Jarret's ideas. Okay, a few more for you. Hudson Hornet. Typically, once the Americans started to get hold of this so-called streamlined style, their cars were big enough to apply it in the way that we'd kind of like to see it done, the overall length and height and stuff, made these cars look very, very streamlined. And they continued right up into the mid-1950s. Now, I guess really, we should say at this point, we have to be grateful to the styling departments, because if you know your history of styling, it was round about the late 1920s that General Motors first established their styling department, and they took this streamlined design to heart, and they kept some of these styles going. The bad news for some aerodynamicists like myself was that they kind of got bored with it in the end, and by the time we got to the late 1950s and 60s, they were going more towards trying to replicate the jet age, which kind of didn't really match aerodynamic performance of road cars. But for a long time, there were a considerable number of so-called low drag, and we're not quite sure how low some of these were. Certainly the aspirations were there, and they were certainly a lot better than the very angular designs of the majority of road traffic at the time. So here's the question: did we ever reach that magic drag coefficient of 0.15? Well, in short, the answer is we haven't yet, and there's a couple of reasons for it. Okay, so the first one is that I mentioned this proportion thing to start off with. Okay, so if you want to get a low drag car, okay, you have to allow a reasonable amount of length to taper the rear of the car so that the flow doesn't separate off the back of the car, and you eliminate separations from everywhere else in the car as well. Okay, it's pretty difficult to do it in an overall length to height ratio of less than 5:1 or 4.5. But that's actually too long for most vehicles on the road today. Kind of makes multi-story car parking a little bit tricky, and roundabouts and things. So most cars today are around about the 3.5 to 1 ratio. That's cars rather than 4x4s. 4x4s are slightly worse. But over that sort of length, you can't actually generate the shaping that you really want in order to avoid the flow separating away from the body. And that's the thing that actually causes all of the drag problems. So although we're trying to adopt that teardrop kind of shape, actually achieving it has tended to be fairly difficult in the overall vehicle lengths and styles that we've had up until now. However, the good news is we've come close in a few occasions. Okay, now there's a bit of a question mark about the actual measured drag coefficient of this vehicle. This figure was actually published in a paper that was written some time ago. The car was actually tested by my former boss when MG were looking at actually doing more land speed record testing back in the late 1990s with different vehicles, and actually the drag coefficient was considerably higher than that. But effectively, it was still fairly low. It's still a cause to that general Jarret sort of shape. And you can see with a relatively small and low-powered engine, the speeds that were achieved both by Stirling Moss and Phil Hill were fairly impressive. And if you want to see the car, it's in the Heritage Museum now, so it's still worth having a look at. Again, the proportions of it are absolutely brilliant, so really good. For road cars, well, the closest one I've found so far in terms of practicality, apart from a couple of concept cars, so something that's of a reasonable kind of length. With these prototype cars that were built by, or for Alfa Romeo by Bertone, and the best one, BAT7, a drag coefficient at 0.19. And it still is a relatively conventional shape. I think there's some clever flow stuff going on there, but that's to be investigated, as it were. But it's a conventional shape and relatively well achieved. So the big question is, why have we ended up with the car shapes that we have today? Well, there's a number of things, really. Firstly, as I mentioned before, kind of that streamlined style went out of fashion as far as styling departments were concerned. And generally, after the mid-1950s, there was no real pressure for aerodynamic efficiency to be incorporated. And so we kind of lost our way a little bit. However, one thing happened which was really good news as far as aerodynamicists were concerned, the 1970s fuel crises. Okay? So basically, manufacturers all of a sudden realised we need to make our cars more efficient, and aerodynamics was one of those things that was a relatively short lead time item. It could be introduced at the next facelift or the next model, and there was some substantial gains to be made. The other thing that happened around about the same sort of time is that because of its level of importance, manufacturers decided to introduce dedicated aerodynamics departments. Okay, up until then, aerodynamics had really been a function of either styling or just an add-on for a chassis guy or a body guy. But now we actually have people that were dedicated to the task, could spend all of their time actually doing some aerodynamic development work. The bad news is that actually the job became more of a service function. So there was no design or release responsibility for any of the work. It was a test and report back and advise type role, which has its limitations. And actually, what happened as a result was that within the aerodynamics community, the task was really to make a car aerodynamic, but don't change the shape, which is kind of a bit of a hard task, really. Okay, so what happened? Well, this kind of slide really defines a little bit of what went on. So with these departments that were now established, the role was really to do what we call optimization of details, which is a technique that was largely started off at VW, but pretty much grew throughout the aerodynamics community fairly rapidly. And the point actually I'd like to make here is that the aerodynamics community in Europe is small. Okay, I think I worked out that pretty much if you put all of the aerodynamicists from all of the manufacturers in Europe together, that would still be less aerodynamicists than people like Ferrari and McLaren have in their F1 teams. So it's still a relatively small group of people. But the good news is they're prepared to share information. They publish quite a lot as well. And pretty much we all know each other as well. So it helps a little bit in terms of technical exchange. So this optimization of details method is effectively making small changes and looking at the aerodynamic effect of those small changes in a progressive way. So when Audi came to look at the Mark III Audi 100, the things they looked at were things like increasing the boot height, changing the screen rakes, but all in a very gentle sort of way. So they took an existing design and they evolved it, they morphed it, if you like, but only by small amounts. And that's pretty much been the trend up until now, that everybody's pretty much gone for that small change. The great thing is that Audi did a really good job. To some extent, historically, it actually saved them in terms of their company performance. It was a key car as far as they were concerned. And if you can remember back to 1983, there was quite an interesting car commercial with a Audi 100 with parachutes on the back. Well, if you want to see it, both that and the one that was in 1984 are both on YouTube. You can remind yourself of those. But the real key for it was the first production car with a drag coefficient of 0.3. Now, typically cars in that era were around about 0.4, 0.42. Okay, so this was a substantial drop. And so much so, and they were so pleased with it, that effectively they put that CD equals 0.3 in one of the rear windows as well, the rear quarter light as a badge. certainly for the first year and a half of production. There's a little bit of a common theme here in that Audi have had that interest in aerodynamics for a long time, even though they only actually had their own dedicated tunnel commissioned in the late 1990s. I think 98 it came on stream. But they still did an awful lot of work using commercially available facilities. The Audi A2, launched in 1999, still has an impressive drag coefficient today. And the great thing about it is that it's a good aerodynamic performance in a very small package. It's a tiny car, if you've seen it. But the shape's absolutely right, and the amount of effort that was spent on getting it right was good as well. So it does prove that you can, in theory at least, get a good figure out of a small car. So, mentioning about tunnels, I thought I'd just tell you a little bit about the facilities that aerodynamicists have available to them today. Some of the best facilities are in Europe. Certainly BMW probably have the most advanced couple of tunnels in Europe now. Wind tunnels are able to simulate moving ground, so we have effectively a belt that runs underneath the car to give us that simulation not only of the wind passing over the car, but the car passing over ground as well. And we can rotate the wheels at the same time. There's all sorts of other advanced test methods in the tunnel, but BMW have got the longest centre belt in 10 metres, which makes their tunnel one of the biggest in Europe. And the pressure's on those guys now. They've spent a lot of money on this tunnel centre, and talking to them when the tunnel was launched, the kind of the joke was, well, okay, so you spent all this money, now your directors are going to be expecting you to make some substantial reductions in drag, and that's actually quite a task for them because their cars were pretty good up until that point as well. This is BMW's so-called model tunnel. So it depends a little bit on what type of work they're doing, but effectively they'll be using 40 or 50% scale models on a very large moving belt, and the belt's so big that you can actually put a full-scale car on as well. So their model tunnel nests inside of the large tunnel in terms of the return circuits for where the air goes, but their German touring car, the latest DTM car, was tested actually on their full-scale moving belt. This is one of my kind of favourite tunnels at Pininfarina in Turin. Pininfarina's continuously led the way in terms of tunnel development. They were the first people to put a moving belt system in their tunnel. They're actually on their third generation of moving ground plane system in the tunnel. And the picture in the top left is actually what we call the T-belt. Now, most moving ground systems just have a narrow belt that runs between the wheels. In Pininfarina, they've extended that and put two further belts either side, which give you a much better simulation of airflow onto the car across the full width of the front bumper, which is a critical area as far as getting low drag is concerned. And certainly if you're looking at doing race car work, then again, that width is critical for you as well. The picture in the bottom left, you might wonder what those things are. One of the big problems about wind tunnel testing is that wind tunnels were basically developed from aeronautical tunnels, which had very clean and smooth airflow. Well, that's pretty good, apart from the fact that on the road we never drive in still air. So there's an increasing demand to try and simulate a more unsteady effects in tunnels. And those particular devices are some flapping vanes, they're carbon fibre vanes, which can flap in phase, out of phase, can do all sorts of crazy things to simulate crosswinds. They can actually look at if you've got a race car in the tunnel, you can actually look at simulating a race car following another one just by tuning the flow off of those blades. So effectively the wind's coming past those blades onto the front of the car, and they're hidden up in the nozzle area in front of the car. So pretty advanced techniques that we have available, certainly experimentally. And then computationally, we're more and more advanced. In the last probably 10 years, computing power has advanced so much that we can run bigger and bigger models in terms of complexity and CAD size, and the results that come back from them are increasingly better, and the turnaround is quicker as well. Very rarely now does it take a week in order to compute a solution for one of these things. We're talking maybe a day, maybe less, depending on what you're doing. Now, perhaps the picture I've put in the bottom right with the Audi in the tunnel with the smoke and a bit of CFD and a bit of wind tunnel work is there really to try and emphasise that probably 5 years ago you were either an experimentalist or a CFD guy. The good news is that now most people are starting to think, well, CFD is actually a complementary system to tunnel work. And the more you think in that way, the more you can exploit the advantages of both technologies. It's not one or the other, it's a combination of two. Okay, so the next question was, how do we accommodate emerging technologies? And where's the current legislation beginning to hold us up? Well, there's a couple of key things I wanted to mention really here. The first one is that the measurement drive cycles that we use to measure fuel economy and emissions pretty much underestimate the contribution of aerodynamics in most people's road use. Okay, and I'll explain. Okay, so top left-hand corner is the so-called new European drive cycle measurement. The time base is only 2 minutes, and it's got a relatively low-speed content. The bit above the red line is the bit above the 50 mile an hour limit, so above that red line is the bit where aerodynamics comes into play. But in the aerodynamics community, we've been saying for a long time that actually they just don't represent most people's use. And companies like BMW and Audi have done quite a lot of research to produce their own customer use profiles. And just as a bit of an exercise, the top right is kind of one of my typical drive cycles, which is driving from home down to Coventry, and the blue crossed area is all the time I spend above 50 miles an hour over a 2-hour period normally. Okay, so actually significantly more than implied by the legislative drive cycle. Now I know that's not necessarily typical, but it is for me. Okay, so aerodynamics is kind of more important for me than anything else. So it depends on your use, depends on everything else, but pretty much those original drive cycles were developed to solve an urban emissions problem. Okay, so they're not really designed for what we're trying to use them for, which is a measurement of general efficiency. But Audi took a bit of a look at this, and what they've actually shown there on those two graphs is that the importance of aerodynamics to Audi customers is much greater than it appears on the legislative drive cycle. So if we base all our calculations currently on those drive cycles, we are underplaying things quite a bit. And I wanted to chuck in another one here that Audi showed as well, which is actually, if you take into account regenerative braking, so you can recover some of those low-speed losses anyway, aerodynamics again becomes a much bigger proportion of that total energy loss. So if we're looking to future technologies as well, aerodynamics potentially comes in as a bigger player in both of those topics. A couple of other little hobby horses of mine, door mirrors. Okay, so afterwards, if you'd like to come down and look at these two vehicles here, so the microcab has, I think, old Metro mirrors on. The Peugeot has door mirrors on that are to current legislation, and they're huge. Okay, so we'll talk about those in a second. The other one is what's happening in terms of crash and pedestrian impact as far as aerodynamics is concerned, and that's a little bit hazy, but I'll try and point out a couple of issues that we think are of concern. Okay, so door mirrors have got bigger. The requirement is for more rearward visibility. That's fine, except for they're huge. Not only are they huge, they create drag, they create wind noise, and in some cases, certainly in a lot of sports cars, they actually block forward visibility out of the door as well. For a long time, people have been suggesting having cameras on their cars, and they don't need to be external. They can be hidden within the bodywork. They can be put all over the place. If the legislation would allow, we would actually potentially get better rearward vision because we can do more. We can play stuff with night vision, all sorts of crazy things. The only real confusion is where you actually put the screens inside the car to actually see the thing. But I think it's about time we kind of move towards this kind of thing. We've got cameras on the cars already for parking, all sorts of other tricks. Why not use them and actually do something beneficial? It looks like pedestrian impact and some crash legislation is starting to influence the shape of the noses of some of these cars. Other people will give you a better idea of this, but certainly some of these so-called nose cones, like you've got on the Ferrari, where the bonnet trim line is actually further back than the leading edge of the bonnet. Latest BMW 3 Series, 5 Series have all got the same kind of thing. And actually, if you then look at the cars in plan view, some of the shaping, which is kind of emphasised on the A5, where you've got this very chiselled front, it looks to be a pedestrian impact equation. Now, bizarrely enough, some of those things are actually working for us, but all we've got a concern about is that legislation is actually driving more and more shape effects, and when perhaps not getting the best efficiency out of the cars to start off with. So those are kind of three of the biggest things as far as I'm concerned currently in terms of legislation and what's actually limiting some of the aerodynamic development. Okay, so next question Brian asked was, will we still have personal cars, or is there a different business model? Well, again, and this is personal kind of view here, but there are one or two interesting things to come out of it. Okay, so first of all, my belief is that we don't really have a fully integrated transport system. So we're not looking at linking one form of transport to another. There isn't one solution that meets all. Okay, potentially there's an opportunity to do lots of pretty good things. You might have seen this one already. So in California, they've been looking at what's called platooning for years and years and years. It's kind of makes an aerodynamic virtue out of congestion in a way. Okay, I think my word of caution is please don't try this on your way home. Okay, you need to have cars that are controlled by the one in front. And there's another question mark on this, is that basically all the benefit is for the cars behind the lead one. So you probably wouldn't want to be paying for the fuel in the lead car if all the people behind you are getting the benefit of how much you're spending. So quite how you adjust that expenditure is another question. But certainly if you drive regularly on the motorways, you know that trucks tend to get close to each other and they get some of that drag benefit as well. So how many cars you have in a platoon or what vehicles are in there is still the subject of quite a lot of research. Certainly there's a benefit to it. One of the interesting things is you have to be a little bit careful if you mismatch the shapes of vehicles. So different shapes of cars, whether it be SUVs, 4x4s or small cars, if you mix and match those in the wrong way, you won't see the full benefit of the system. And of course, effectively, it does rely on quite an advanced telematics approach as well. So we're kind of a little way away from some of those things. Yeah, sure. Okay, so a couple of things then to jump onto. So why not take a bike with you? Is kind of the interesting thing now. As we said before, more and more common to see bikes and stuff around. The interesting thing is that in London, apparently 7 miles an hour is about the average speed of most passenger journeys. Okay, well, I'm not quite sure whether Boris will reach it, but if you go a little bit more quickly, somewhere in region about 80% of the energy you use is down to aerodynamic resistance. So maybe there's a job for some of us there if we need to in terms of advising some of our road customers. Interesting thing is if you start to look at bikes and electric bikes, why not if you use your regenerative braking to charge batteries to charge your bike? So when you get out of your car, you take your battery out of the car that's been recharged by your regen braking system, stick it in your bike, and away you go. Similarly, I don't know if you've seen some of these, there are more so-called adult scooters around. Again, these can be passive or they can be fully powered solutions as well. Okay, so let's jump back to a couple of things in terms of road cars. So what do we think we want to get out of road cars? Well, two things really. One is we really want low drag, streamlined cars to come back, and secondly, we want some kind of proportions. That's pretty much a split of, and it's not necessarily for that car, it's a generic split of where the drag comes from. And the real key is that 70% of that aerodynamic drag comes from styled surfaces. So if you thought that aerodynamics was independent to styling, then you're wrong. There are a few cars out of the market currently, or ones that are about to come into production, which have some overtly aerodynamic forms. The BMW i8 is one. Clever one with this is it's got very narrow tyres on, but the designers have disguised that. People don't read the fact it has very, very narrow tyres. So there's a good little trick there. The VW XL1, great car to look at. It's only when you look at it from a rear three-quarter view you realise it's something strange going on. But proportion-wise, it's actually the same size as a Polo. VW have never actually shown the two together, so the height thing's a little bit of a confusing issue, but it's something to look out for, but still a fairly impressive performance. Whether you like this in terms of style or not, that's entirely your choice, but some impressive figures over what is a conventional looking car, but it has some clever tricks on it to play as well. I mentioned frontal area at the beginning. It's still a problem. I think we've kind of forgotten what small car means all of a sudden. Okay, so frontal area is still an issue. We still need to think about it. It's kind of out of our control a little bit. Maybe with newer materials we can reduce some of the crash requirements, and we can get back to a smaller car again. Attribute this comment to my former boss at Rover, Jeff Howell, and it's absolutely true that once the style is set, then effectively so is the aerodynamic performance of the car. So that bit between styling and aerodynamics being intrinsically linked is still there. I'll just quickly show you. So that optimization of details technique is actually taking the car and working down in terms of drag. It looks like we're asymptoting towards a limit of about 0.22 in terms of drag coefficient. So if we want to go lower, we need to start looking at working up from the other direction. So the key, as I said, is really for aerodynamicists and designers to really work together. My personal belief is that styling and aerodynamics need to be a fully integrated department, not two different things. Thank you.
Thank you. Thanks very much, Jeff. I found that a fascinating talk. It's a relatively secret history, I think, aerodynamics and its effects on vehicular design. I was reminded that the person many of us consider to be the founding father of modern industrial design, Raymond Loewy, made his name originally by taking aerodynamic theory and applying it to stationary objects like fridges and toasters, miraculously. So thank you. We move to our last speaker, and we're entering the realms of education now. Nick Hull is the Transport Design Course Director in the Department of Industrial Design here at Coventry. He's also Director of NHD Limited and Associate Editor at Car Design News. And his title is Using Future Scenarios, A Glimpse into Perpetual Motion and Urban Colonies. Nick.
Thank you, Martin. Okay, what I'd like to talk about today is just how we promote creativity in our students here. Today we're celebrating kind of 20 years of Coventry University becoming a university from a former polytechnic. But we're also this year, 2012, celebrating 40 years of transportation design here in Coventry. And in that time we've established a great reputation for producing well-rounded students for design studios all around the world. Now, part of that success involves educating students to really think about and embrace the challenges of the future, not simply just styling the next generation Jaguar or Aston Martin sports cars. However, asking students to design a vehicle for, say, 2030 is in many ways pretty meaningless if you're attempting that in isolation. And after all, how can you be expected to understand even a fraction of the technologies and constraints that might impinge upon that vehicle? So to counteract that, our transport and automotive design teams, we've really pioneered the use of future scenarios to provide a background for our students' creativity. And that enables them to frame their ideas within a very controlled context. Now, I first came across future scenarios when I was working for sort of 10 years for Honda. In the 1990s, and we used future scenarios quite a lot, and they're still used a lot within Honda for their advanced projects. And we've introduced it here in the last couple of years for our final year projects and postgraduate students. Now, as the government's think tank on science and technology issues, Foresight investigates the challenges and opportunities for society. And this is the scenario document that we currently use in the department. And the intelligent infrastructure systems, this focuses on future transport for the UK. And it draws upon a wide range of sources, such as reports from government departments, utilities operators, and journals such as New Scientist or The Economist, and so on. Now, in developing a future scenario, you firstly need to identify what are called the drivers of change. We've heard that this morning already from Professor Bailey's film. Now, you can think of these drivers of change as the sides of a cube, and it's a box in which you can frame your ideas. And there are basically 5. There's a political component, a technological component, social, environmental, and economic components. Once you've from assessing the drivers of change, you've then got to identify what are called the 2 axes of uncertainty, and Foresight uses these as a horizontal axis, which is the availability of transport that has a low environmental impact. And this is basically a technological and environmental and economic axis. And then a vertical axis, which is the degree of acceptance of an intelligent infrastructure. And after all, in a democracy, how are you going to persuade people to sign up to those new technologies? Will they pay for it? How are you going to persuade them? You can't force them. And just to put it in context, in 2012, we're sort of on a midpoint. We have pretty high impact transport. It affects our lives tremendously. And we're at a fairly neutral point on the infrastructure axis. Now, while these scenarios don't purport to predict the future, what they do is to allow us to see how certain combinations of events and discoveries could change the future. And as such, they allow us to sort of see what we might need to prepare for and the opportunities that await us if we choose the right path ahead. And those 4 scenarios are called good intentions, perpetual motion, tribal trading, and urban colonies within this, the foresight scenarios. I'll just take you through a couple of these, just to show you how we use these as tools to promote creativity. First, this first scenario is called perpetual motion, and in many ways this is the sort of idealised future that we see a lot in films and TV, the kind of Hollywood approach to it, Minority Report or Tron, for instance. And a precondition of this always-on 24/7 world of perpetual motion is just limitless energy supply, emission-free and preferably pretty low cost. And this scenario foresees investment in a really comprehensive hydrogen infrastructure during the 2020s through a mix of UK government and the large oil companies. And in this scenario, people are just too busy to think about the efficient use of energy. And things like stress are a major health problem. Stress becomes the new obesity for that generation in the 2020s. And so after the scenarios, which we spend a couple of days introducing to the students in detail, we then hold a series of discussions to generate ideas for vehicles and to tease out those underlying issues. What are the issues there, sort of in orange, for some possible transport devices? I'll just take you through a couple of more examples in detail just to show you how those might be visualised. That's the area that we're good at, is visualising and actually giving shape and form to those futures, not just words and data. Here's one from a year ago, Honda Petto, which is the idea here is a soothing self-guided vehicle for that stressed out, hugely stressed out Generation Z of the 2020s. So for these customers in 2025, these platooning vehicles with calming scented cabins, massaging seats, they're that little luxury to look forward to at the end of a stressful shift. So it's quite the opposite of sort of commuting on the tube today, for instance. Of course, just another shot of the finished vehicle there. With the fuel cell infrastructure, that does allow vehicles, actually, you've got vehicles which are miniature power stations, effectively, that could provide power to your apartment as well. And another example here was a postgraduate student, Tom Watson, who proposed vehicles that would then dock to the building and provides an extra relaxation sort of pod that adds onto your apartment as well. And you're sort of adding to the visual language of the architecture of cities in that way as well. Second scenario I just want to show you is called urban colonies. And this isn't quite such a rosy picture here. There's no big, huge investment in clean technologies going on here, but good environmental practice is right at the heart of the UK's economic and social policies here. And maintaining our existing standards of living is possible, just possible, but at a pretty heavy price. There'd be a heavy reliance on biofuels, and so vast agricultural areas of, say, East Anglia, the East Midlands, Scotland, and so on will be given over to that, and we could just about create that infrastructure then. With this one, we have really quite sustainable urban areas which are developed, and these become the most popular areas in which to live in and cost-effective areas to live in. For instance, the West Midlands from, say, Wolverhampton through to Rugby, where we are here, would become more popular to live, or somewhere like Greater Manchester. What would suffer would be living in the countryside. So living as I do, or Steve does, down in the Cotswolds, where kind of we live, and commuting 50 miles to London or into Coventry would really become hideously expensive and very heavily taxed, because under this scenario you'd be taxed on what you consume in terms of energy, not on what you earn. So within the cities, life can be pretty good with this scenario. It's actually quite attractive, arguably better than we have now. There's much more equal sharing of road space, much less noise, of course, less pollution, widespread use of electric assist bikes and mini vehicles, much better public transport, a kind of future Amsterdam type existence, as you like, as we've seen earlier on with John Jostin's presentation. And in this scenario, there would be a real trend away from owning something as large as an actual car. And you'd probably have access to a range of small city vehicles. In addition, you'd probably belong to a car sharing group who invest in a pretty expensive fuel cell car. And by pretty expensive, it might be £70,000, £80,000 in today's term, so you'd have to share it. And intercity travel would be mainly by shared transport, high-speed trains, more high-speed trains, limousine coaches, a little bit more like urban Japan is today. If you've ever been to Japan, that's the way people travel long distance. So of course it's not just about doing styling sketches of cars. That's maybe what we're best known for, but it's not what we're all about, and that's in terms of educating students. We put a lot of high emphasis on really high quality visualizations of the whole scenario, depicting the look of the whole city and giving form to what that future looks like. And the emphasis here is on really quick ideation, fast sketching, storyboarding, building up concepts in small groups over a few days. Just a few examples here of that process kind of going through. Another solution within this scenario would be these kind of platooning town buggies, where electrical power is shared to reduce the electrical drain once you've got the momentum going. They might be made of very lightweight renewable new composites, such as basalt fibre, for instance. And of course, with more ageing populations, we're really going to be satisfied by current mobility trolleys with tartan seats and little dogs in baskets like we saw earlier on. I think not. I think we're going to demand something a bit better than that, something like a bugster to get around in future. Another idea would be vehicles could fold up and store. There'd be quite new formats of family vehicles, maybe vehicles that can divide from one larger vehicle and divide into smaller devices for individual journeys, like the vehicle you see below there from Constantinos, a postgraduate student from a couple of years ago, where the whole vehicle can divide into a series of bikes, cars, but can nest together to form one big vehicle as and when you need it. Another group of students proposed that we might have really tall delivery trucks, and going right back to what Steve was saying at the start of this morning. Those would be very advanced telematics and these huge trucks that can just ride slowly over the other vehicles in complete safety. Those trucks could split into smaller delivery pods for restricted inner city areas. And in those more depleted rural areas, we might have much more functional, rational vehicles that again would be shared within communities, such as seen on the right with fold-out transparent solar panel doors. So these would be the kind of new Kangoos and Berlingos of the 21st century. Another concept here, looking at from last year, was Akash Patel's Creo concept. Again, a fairly typical kind of outcome from students in terms of something with fully recyclable body panels, a very lightweight tubular frame. It doesn't require painting or welding, for instance. And in this kind of scenario, with very advanced full car-to-car telematics and very slow-moving traffic compared to today, we could reach that new area. We have really lightweight, flyweight, Gossamer-like cars. And it could be great, fantastic opportunities here. And in future, we might regard today's VW Golf or Ford Focus, a 1.5-ton just dinosaur monster, in the same way that we regard steam locomotives or traction engines today, or an early IBM mainframe compared to an iPod in today's terms. If we're going to have more high-speed trains to replace aircraft for short-haul journeys within Europe, they better be good-looking, a lot better looking than the Eurostar I was on yesterday, for instance. An example here is one from last year from Chris Scholes. Another project here within this scenario was this remote-controlled zero-emission construction machine for very crowded urban construction sites. And this is really addressing the problem of safety with an increasingly ageing construction workforce, which is a problem we have in this country. And it would allow those remote control devices to do the majority of work that humans don't wish to do, such as mining underground, or it could be decommissioning nuclear power stations in future. In the early stages of sort of concepting, it's really better not to eliminate those kind of crazy ideas too early on, just allow students to run with them a little bit and develop them and flesh them out a bit. One group of students here developed ideas that used the waste heat from buildings as a source for a new weekend sport, kind of urban hang gliding, if you like. And they developed these ideas of air scooters that you could scoot about on and use the hot air to transport your way around. And of course, the key difference here is that you've got a built-in spectators there in the buildings with viewing galleries. And this is something that's a bit more fun and poetic. Indeed, it doesn't have to be all kind of hair shirts with this kind of scenario. We should be able to still have fun. We're going to want to have fun in the future. We're still going to want our motorsport. It might be new types of motorsport, such as these urban dirt track races, vast monowheel dirt track races, as a new kind of urban sport that we would want to spectate at. So again, visualising those, good use of Photoshop and high-quality visualisations is what we're all about with this. Other scenarios that we haven't got time today to go into address other issues of global warming and flooding. For example, Simon Laumet's project from last year of a solar-powered desert vehicle for the Middle East, rather than tearing around the Middle East in a Mansouri decked-out Bentley or Range Rover, it might be something like this in future. Or Jack Allenet's project from last year, an amphibious rescue vehicle for flood zones, where the whole form of the vehicle and the way it actually unfolds allows it to scoop up cattle and villages from flood-affected regions such as Pakistan or Bangladesh. We're certainly going to have more and more problems with floods in future. And even us in the UK as well, floods are going to become a much bigger part of our daily life. So the whole format and the architecture of such vehicles are totally different to the things we're used to today. Okay, so just to recap on this, the whole point of future scenarios, it gives us a literal framework, a clear context for student projects, and very often students at the start of this process really resist it. You're restricting us, you're giving us constraints, don't do that, allow us to be free. But actually, designing without constraints is a bit of a waste of time. And it also helps us to just align our goals with the university's grand challenges in terms of research. And you might think of those grand challenges as major sort of rods within this framework or this scaffolding that allows you to frame your idea. And your individual project is a certain sort of space within that framework. So putting the whole thing together, this gives us a really quite useful tool that allows us to explain a clear context to the students for final year advanced projects, and just allows them to get on with the job of creating really beautiful and desirable products and building them up over a period of weeks and months. The other thing that from our point of view as tutors it allows us to do is it gives us a much better, it allows us to guide them towards much better, more resolved designs. It makes us easier to interrogate the outcome, to measure it and assess it correctly, much more thoroughly than we used to do in the past. So just to conclude on this, the vehicles that developed under these kind of new constraints, they don't have to be dull or boring. That's the important thing. By contrast, they should be really fascinating, exciting vehicles. That's what we're all about here. Our vehicle makers, going back to what Steve was saying at the start of this morning, vehicle makers in future are going to really need two attributes. Firstly, to entice customers, particularly through design, to buy their products, whatever they may be. And secondly, to communicate the values of that brand, again, chiefly through design. And it's about communicating those visions of the future to the wider sort of audience that's important through really good visualizations of the future. So yes, these ideas that we've shown here are kind of imaginative, hopefully, possibly fanciful. But that's what we're all about here in Coventry, and we're determined to remain at the forefront of this debate and to continue to be a key supplier of young designers who can meet the challenges of these coming decades for the next 40 years. Okay, thank you very much.